Well, let's go for our final talk. Então, nossa última fala de professor Argyris Arnellos, que é um pesquisador visitante no Departamento de Lógica e Filosofia da Ciência na Universidade do País Basco, na Espanha, vinculado a um grupo importante de filosofia da biologia, que é o grupo de Álvaro Moreno, e tem publicado uma série de artigos sobre função, agência, autonomia. Eu tenho a honra de ser coautor de 2 artigos com Argyris, e a honra maior ainda de ser amigo de Argyris. It's an honor to be your friend, my friend. So, Argyris will speak to us. É para falar em português agora. Argyris nos falará sobre a autonomia como uma propriedade que define indivíduos biológicos uma perspectiva colaborativa. Argyris, please.
Thank you very much, Samuel. Well, hello everybody. Can you hear me? I know I will be heard a bit typical here, but I would like also to, first of all, thanks cordially everybody for this wonderful hospitality, the chance that they gave me to visit the country and the university. I'm really amazed from all the work that you have put here, and I feel really very honored and very lucky that I met all the wonderful colleagues, students, researchers, and of course I had the opportunity to meet and make new friends with all the other guest speakers and invited researchers. So, once Arbel, I would like to make a bit of an introduction here. Once Arbel just wrote me an email and told me, look Argyris, I would like to come and give a talk and help us in this thing here. I said, Arbel, my friend, with pleasure, but I know nothing about ecology. He said, no, don't worry, we're doing a lot of things here, epistemology, we're doing functions, we're trying to build theoretical models, we are going into philosophy of science, into philosophy of biology. I said, yes, but again, how can I relate all these things to ecology? He says, don't worry, okay. I didn't need too much in order to persuade it and come here. Then I came here and I saw that, with great pleasure, that a lot of the things that I can speak and I'm researching on my own are highly related to what you're doing here. Of course, that was a great relief. And another relief was that I saw my colleagues and others, researchers, invited speakers, talk today, and I really think that what I would try to say today is highly related to what they have said. In order to try to give you a scheme of how I have in mind the relation to what I'm going to talk with what they have taught, I would just like to say that as Greg and Stuart have said, the way we approach living systems, agents, individuals, collaboration, altruistic behaviors is a naturalized attempt. That means that we try to ground phenomena, complex phenomena in sound scientific theories, and to base on these theories in order to provide a different language, a language that will abstract complexity. Now, how do we relate, how my talk specifically relate to what Steve and Alejandro has just presented today? Well, that was for me a very good fast-track lesson in individual-based modeling. What we saw was that the models and the systems that they are studying is systems that at the level of the individual we have, let's say at the level of the parts of the system, we have individual agents doing their own things, behaving in their own way. And at the level of the whole, we're getting an emergent behavior. Well, the characteristic of these systems is that the behavior at the level of the whole is an emergent behavior, and it follows what we say a multi-level selection type 1. That means that the fitness of the whole, at the level of the whole, is just the sum of the fitness at the level of the parts. I hope I have understood that correctly. So what I will try to show today is that, and of course, this does not make the whole an individual organism on its own. So we have a school of fish, a flock of birds, or a pile of ants. They are individuals on their own, but the whole is not an individual. What I'm trying to discuss today, and this is actually my main topic of research the last 6-8 months, is when we can say that when a group, an aggregation of biological entities at any kind of different levels of complexity, let's say cells to multicellular to societies of animals, and animals to societies of to other kinds of societies. When we can say that a group of individual biological entities form a new biological individual. Now, I hope that what I will try to present and to suggest here is what can be the missing link, or a part of the missing link in between the two levels. So, well, a brief outline of what we are going to see. We will begin with some collaborative approaches to individual organisms. We will try to see the three main approaches and how they deal with individuality. Then we will discuss, we will explain why the whole problem goes to function and functional integration. Then we will discuss function in natural selection and in adaptation. We will try to see how and what does it mean to explain function under these frameworks. Then we will try to say why we suggest a function, an explanation of function through an organizational perspective. Charbel, I think, said something in his introductory talk the first day of the meeting. We will present a model of minimal functional differentiation. That is, we will try to present a model of function which is compatible with the organizational perspective. We will discuss how this can be applied to multicellular groups. Then we will use this result to discuss why we think cyanobacteria and volvox, if we see them as two groups of one is bacteria and the other is eukaryotes, cannot be rendered, cannot be classified as organisms, but they are just groups of cells. Then we turn to development to discuss a bit why we think it is important. And then we will, I will try to show, but very quickly, what's happening in the development of metazoan as a paradigmatic example of organism, what kind of regulatory mechanisms arise there, what kind of functionality we may have, and to conclude. Well, I have a lot of information in the slide, so some of it I will read it, some of it I will just describe and you can read it, some of it I will read it and go through it. So, Dupré and O'Malley, in a very provocative paper in 2009, said that forget individuation, forget organisms, forget autonomy, everything is collaboration, everything is interaction. Rather than reducing cooperation to surfaceness, they suggest surfaceness and cooperation that might be better understood through what we say a framework of collaboration. Now, by collaboration they mean interactions between components of systems that lead to different degrees of stability, maintenance, or transformation of the system. They are quite radical, so they are discussing also cases of prions, plasmids, organelles, viruses, and other kinds of symbiotes and endosymbiotes as cases that achieve a great degree of interaction, which translates into a collaboration in the metabolic level. And they conclude that since we have such a collaboration at the metabolic level, then we cannot discuss about individuation or organismality or autonomy. Everything is collaboration. Of course, I'm simplifying things here in terms of their arguments, but more or less the message is this. For instance, they take the cases of Dictyostelium, Discoideum, and Serratia coli. One is the unicellular amoeba, it's a eukaryote, the other is bacteria, it's a prokaryote. And they discuss their formation in biofilms. And they say, well, what we can say for these communities, for these groups? They express a well-defined self-organization. They present division of labor that includes specialized cell-to-cell interactions. There is suppression of cellular autonomy at the unicellular level and end of competition. There is metabolic collaboration, combined defense and attack strategies, and coordination of movement, of growth, and of reproduction. In all, there is a bunch of things that on their own, the unicellular parts of these groups could not achieve. So, overall, they should be considered as multicellular organisms, and there is a deep and extensive collaboration independently of any actual conflict, because as we will see later, there are other approaches to collaboration that they discuss actual conflict, so they are discussing the trade-off between collaboration and conflict. A deep and extensive collaboration independently of any conflict between biological entities blur at the very least any distinction between so-called individual organisms and these larger organismal groupings of which there are parts. Now, in another very influential paper of 2010 by Forster and Ralph Garden, they kind of try to provide a three-party, a nested three-party approach view to biological individuality. So they say an organism should, in order a group of entities to be classified as an organism, as a new individual, should satisfy three views. The first view is the alignment of fitness. The alignment of fitness defines an individual organism as a living entity in which the fitness interests of its components are aligned such that little or no actual conflict is expressed. Well, okay, there are many ways to achieve that, but the most common and known way is the unicellular bottleneck. When the components of an entity are genetically homogeneous, there is no conflict of interest and cooperation is unproblematic, or if you like, there is big probability, there is virtually there can be high cooperation. Of course, this is not true all the time. The second view is export of fitness. So we align fitness to have genetic homogeneity, but that is not enough, because you may know that there are two main ways for a multicellular organism to form. The aquatic and the terrestrial. The difference between the two is that in the aquatic way, what you have is incapability of absolute separation after the division of the cell. And this is more probably due to the rigidity of the filament or of the cell walls. Or you have multicellular aggregations where the multicellular group is formed by aggregating unicells, and then in this case you may have lower genetic homogeneity. So okay, according to the first view, you could say that, well, I don't care about cellular differentiation, I don't care about germ-soma separation or whatever. If I just have many cells, the one linked after the other, and they are somehow connected, then I have a multicellular organism. So this is not enough for them. They say that you need also to have export of fitness. And according to this view, an individual organism is defined as a living entity in which the components are interdependent on one another for reproduction. So I may be aligned with my neighborhood cell, I may exhibit a genetic homogeneity, but that is not enough if there is no interdependency between the cells for reproduction. And in order for such interdependency to be achieved, usually the method that multicellular groupings are put on is germ-soma separation. This is what, I don't know if you are aware, but this is what's happening, for instance, and the paradigmatic example is Volvox carteri. In Volvox carteri, Volvox is a multicellular green algae. The unicellular ancestor is the Chlamydomonas. You know it better from me. So what is happening there is the following. The problem is in terms of adaptive capability of the unicellular part, is that it needs to photosynthesize, and in order to photosynthesize, it needs to be it's floating in the water, so it needs to be not deep but on shallow waters, on the upper part. But in order to do that, it must also swim. it must propel the flagella. Propelling the flagella is incompatible at the same time with photosynthesizing due to the mechanics of and the morphology and the physiology of the chlamydomonas. So what they have, let's say, evolved in the multicellular case is that you have a complete germ-soma separation. We have the big gonads, which are responsible for reproduction, but they cannot swim, and you have the somatic cells that they can swim, but they cannot divide. They are terminally differentiated. So this is a case of complete germ-soma separation. And in that case, if you understand, you have export of fitness, and that means that in order for the fitness of the whole is totally decoupled from the fitness of the part, because the fitness of the somatic cell is zero. The somatic cell cannot divide, so they cannot reproduce themselves, and the gonads cannot need the somatic cells in order to be able to be at the level where they can get sun and they can photosynthesize. So one could say, but okay, so problem is solved. If you have this, you have a kind of functional integration between germ and soma, and then you have the third view, the third prerequisite, and then you have a full-fledged organism. What I will try to show is that this is not the case. So the third view is that an individual organism as an integrated functional agent is an integrated functional agent whose components work together in coordinated action analogous to the pieces of a machine, thus demonstrating adaptation at the level of the whole organism. Now the organism must display adaptation at the level of the whole that are not present at the level of the components, and if that is the case, then there is evidence that the whole organism is the locus of fitness. Well, the challenge then is to understand the transition, in order to understand the transition to complex multicellular individuals, is to explain division of labor, as we just discussed about Volvox, especially between germ and soma. Once fitness has been exported by germ-soma specialization, other forms of specialization are free to arise within the soma, thereby allowing for increased functional organization and organism level adaptation. According to this view, they classify many organisms, such as Volvox as an organism. They say that the Dictyostelium is a very difficult case, which would better be considered as a social group due to too much competition, although requirement 2 and requirement 3 are satisfied. Colonies of polyps are difficult to say and assess, and the list goes on with verdicts that, as we will show after presenting the third approach to collaboration, are not uniform in their results. Now, the third approach to collaboration and to organismality, it's coming from Strassman and Queller and Strassman. They have two papers. One is 2009 and the other is 2010. Now, what they say is that we don't care about what is going on between. We don't care what is possible to go on between different parts of an organism. What we care is what actually is going on. So I don't care if there is export of fitness or alignment of fitness, because all this gives a possibility of something to happen. I care about actual collaboration and actual conflict. So if I try to lay out actual collaboration and actual conflict, I have four parts. At the upper left part, I have high collaboration. Upper right part, I have high collaboration and low conflict. So in there, all these are classified as organisms. In the upper left part, I have low cooperation and high conflict. So this classifies as societies. In the lower left part, I have low cooperation and high conflict, and this is just competitors. And in the lower right part, just groups. I cannot classify them. So in general, what makes an organism is high and near unanimous cooperation among its constituent parts, with actual conflicts among those parts largely absent or controlled. Now, I will pass some things quite quickly because we have no time, but they are arguing differently than Dupré and O'Malley or than Force and Ralph Garden about specific cases of the E. coli or of the Volvox or of the Dictyostelium and many other organisms. Now, what we have to, of course, what we should keep of all these approaches is that all researchers are trying to demonstrate that there is cooperation and there is some kind of conflict, that it is not enough to break cooperation, so in such a degree that the result will not be an organism. Each organism is itself and should be seen as a social unit that has evolved very high cooperation. No matter aquatic or terrestrial, additional mechanisms that reduce actual conflict are often important in the evolution of organismality. And the essence of organismality lies in the shared purpose. The parts work together for the integrated whole with high cooperation and very low conflict. So, as I said before, it all comes down because in order to achieve high cooperation and low conflict, there must be some kind of interaction, some kind of functional integration, some kind of integration between the parts of the system. So the problem comes to discuss function and explain function in biology. Now, this is not a trivial problem at all. Charbel said something very quickly in his presentation. I will try to go in some more details. There are two, but let's say three approaches to function. One is explaining function through natural selection. The other is to explain function, as we say, collaboratively, but in a phenomenological way, like we just saw that these three cases were attempting, with dissolved autonomy, but seems that they cannot explain function because they cannot explain objectively why they result in different verdicts. And there is the organizational approach to function, where we have an autonomous system which is functionally integrated, while it is also functionally differentiated. The main problem with explaining function based on natural selection and adaptation, which is also what these three cases we just saw used, is that in order to do so, you need some let's say, logical arguments. And the logical argument here is that the organism, all parts of the organism works unanimously and in a way as a machine, designed as a machine. Of course, the result of the design is not a human self-imposed design. This design has a result by the operations of natural selection. And if you have this, then you have an organism. First of all, here there is a problem. One problem is that you need to find and to clarify which are the different levels of adaptation where adaptation and natural selection operates. But apart from that, we think that a fundamental difference between watches, for instance, watch is the example that all traditional philosophy of science provides. Between watch and organism is that watch is formed by fixed components fabricated beforehand and later assembled, while in the organism the parts are formed for and from the others, some parts producing the others. So it's not only that you don't have ready-made parts that you just put up aggregating somehow, it is that some of the parts are being constructed by other parts within the system. In this, we have also to add what Wimsatt has objected as that we are not sure where a part ends and where a part begins when we talk about living organisms. So this is also translates to the sum is more than the whole is more than the sum of its parts, and or other things. But the main message is that. So in the organizational approach to function and to functional integration, defining the parts of an organism requires referral to the role they play in its maintenance or its functioning, and vice versa. An organism cannot be fully understood except in terms of its main constituents and the processes they go through. This type of functional integration results in an implicit normativity. The parts relate to the whole in functional terms. That is to say, the processes by which components are produced and interact are precisely those required for the constitution and maintenance of the organization they integrate. An organism implies a type of material organization in which parts and whole are interdependent, maintaining a rather intricate dynamic relationship. That is, an organism is functionally integrated under this sense, so that its dynamic organization plays a causal role in the generation of the constraints that actually make it possible. So what we have a closure, we have a case where parts are forming an organization because they constrain the processes that make the organization, which makes the same parts. And this is basically a basically autonomous organization, as it is exemplified by a cell. Now, there's a lot of discussion about what we gain, what is the advantage of such an organizational approach to function. But it seems to me that it is very difficult, although, as I said in the title also, it will be a collaborative approach to autonomy and individuality. It seems, nevertheless, it seems that an organizational approach of autonomous individual is important, is indispensable, as it is possible that without a highly integrated and cohesive individual organization, living systems will not be able for long-term maintenance and evolution. And because it seems to be very difficult to provide a naturalized account of concepts like functionality, unit of selection, but also to explain teleology and normativity of living systems. By the way, Greg before asked what is the teleology of the model that Alejandro suggested. I think that the teleology is just a teleology that can be provided by the dynamics of self-organization. So the teleology, as I said in the beginning of the talk, stays there. It does not export it to the other levels. So practically, this kind of teleology, as we will say later, is not enough for living organisms. And that is because there is no only implicit normativity in living systems. Living systems are adaptive agents, and as adaptive agents are an instance of explicit normativity. As we saw, they exhibit an intrinsic norm due to their basic autonomous organization, and they also exhibit the capacity to modify their actions to fulfill this norm better and more robustly. Then we are looking for a type of functional integration, if we want to speak about full-fledged individual organisms, that will allow us to move from an organization that exhibits implicit normativity to one exhibiting explicit normativity. So this, as we will see, implies some sort of regulatory control mechanism operating by appropriately changing and constraining the metabolic processes, but not being constrained by them. So, now some things that let's try now to see. Okay, so functional integration is what we are looking for, and it is a certain type of functional integration what we are looking for. Of course, there are a lot of objections if you are doing philosophy. Finding objections in front of you is the easiest thing. Wilson has some pretty good objections about how helpful can the notion of functional integration be. His problem is that functional integration is something that can be exemplified and operationalized only in grades. So it is this gradual nature that makes the operationalization of the concept almost impossible. For instance, cellular slime molds are functionally integrated, but not in the same degree as a higher animal. A plant and a higher animal may have the same degree of functional integration, but they do not share the same mode of development or evolutionary history. And I would say not even the same capability for agential behavior. The organs of a higher animal are causally and hence functionally integrated, but so are the members of a good music band or the members of a pit crew. So the difficulty lies in the need of specification of the type and degree of complexity of the interactions between parts in order for them to qualify as members of a single functionally integrated whole. So now, in order to go there, how am I doing for time?
Even if you have in total more with discussion, more 50 minutes with discussion. Okay. So 30 minutes. Okay. So
let's go a bit into some not very simple stuff. I will try to pass it quickly because we have no time, but what I would like to show you here is the whole conceptual and the whole logic behind function and how you can define it in an organizational perspective, actually how you can model it, how you can define it. So, first of all, so far we have talked about self-organization. Self-organization is not enough. This is our claim. And it's not enough, we will explain here, because self-organization, as we will see, is a closure on one constraint, or if you like, on the same type of constraints, on the same group of constraints. So, if we want to explain function in an organizational perspective, we have to go to the notion of self-maintenance. Now, the paradigmatic example for self-maintenance is a candle flame. The candle flame maintains a temperature above the combustion threshold, vaporizes wax into a continuing supply of fuel, and in a